Alright, three, two, one. Series part three. Alright, so let's conclude, for now anyway, the story of series. Okay, so kind of what's left to talk about. Well, for this particular video, we're going to be singularly focused. So, given a sequence, we say that its series will converge absolutely if the series of the absolute values converges. And we will say converges conditionally if the series converges, but the series of absolute values fails to converge. Okay, so again, hopefully this is familiar. You remember this from your Calc 2 days. This is primarily what we're going to focus on. We are going to focus on these two concepts, and that's it. That's all we're doing in this video. That being said, we got a bit of a blueprint of what we're going to do. So the first thing we're going to do is verify that absolutely convergent implies convergent. Thus, there's a reason to sort of go, hey, the absolute value converges, and then if it doesn't converge, we can still have this converge. So that's the first task. Then the next one is to produce examples of conditionally convergent series. And then produce some tests about absolute convergence. So speaking of Calc 2, we are primarily going to create conditionally convergent series using the alternating series test, which for us is not really a test, it's just alternating series converge, and here's why. But tests for actual determining of absolute convergence are, of course, the root and ratio test. And then we will finish off with a brief discussion of why is there even a reason to care about the difference between these two. Right, I mean, other than the obvious, there is a difference, because I can create things that are conditionally convergent, so these exist. And as always, if in mathematics, if something exists, it's typically worth studying. But we'll give a bit more context as to why this becomes an important thing. Not particularly for our course, but for later on in your math life, potentially the difference between absolute and conditional is incredibly important. All right, so that's the plan of the work. Let's work the plan. All right, so first things first, we're going to prove absolutely convergent implies convergent. In order to do so, we need to, once again, follow the blueprint that we've been following, which is, let's first prove a fact about partial sums, and then we'll apply that to a fact for series. So, the triangle inequality holds across summations. That's not shocking. And for your homework, I'm going to make you replace this with infinity. And it's not as easy as you think. It's surprisingly tricky. It seems like it should be super easy, but this is the starting point, but there's got to be a scotch clever. But anyway, so how do you prove this? So once again, it's a fact for all n. Not shocking what we do, it's going to be induction. Alright, so of course if I replace n with 1, then just everything works perfectly. The end. So then suppose it works for an m, and then we'll verify it works for m plus 1. Alright, well, m plus 1, we can pull it apart like this, apply the usual triangle inequality, and then imply the induction hypothesis here, and then that's it. There you go. Right, nice, simple inductive argument. Nothing out of the ordinary or crazy, but again, our goal here is to first show that for partial sums things work nicely, and then we'll go to limits and show that the series will behave in a similar manner. Right, which, again, if we're going to talk historically, that's effectively what people did with series. They were like, oh, it works for finite sums, so it should work for infinite. But they basically just took that as a principle. They said that's always true no matter what. But as we've already seen, that's not the case. You need to prove things work for partial sums and then explain why it's going to not screw up when limits show up with series. Okay, so now that we've got this, we will now prove that if you have a absolutely convergent series, then the series converges. So this means that we can actually separate convergence into three classes: absolute convergence, conditional convergence, and then just divergence. Right, because absolutely convergent will subsume normal convergence. All right, okay, and this one is going to be super easy thanks for the Cauchy criterion. So this is, again, another example of, right, this converges to something, absolutely, so the sum of the absolute values converges, but I don't know how that's going to relate to the original, but it doesn't matter. Because given an epsilon, since we converge absolutely, we know that the Cauchy criterion applies. Alright, but this is a positive number, so its absolute value is equal to itself, and we know this is greater than or equal to that, and hey, the Cauchy criterion now applies to the original summation. There we go. Convergence must be assured. Beautiful. So, there we go. The Cauchy criterion once again coming in to help us, and again, shouldn't be too shocking because the sum of the absolute values converges, but right, whatever value that converges to probably has nothing to do with this value. So, a good thing we have a way of detecting convergence without knowing values beforehand. Yeah, good stuff. Alright, beautiful. Alright, so task number 1 completed. We have now proven that every absolutely convergent series converges. So now our goal is to produce an example of conditionally convergent series. So something that converges but does not converge absolutely. Okay. Now in order to do so, we're gonna... It's not gonna be awful. I'm making that little verbal pause there made it seem like it's gonna be bad. It's not. But we're about to. Our next goal is to prove the alternating series test, which again is not really a test. But as we're going to see, the proof of it is surprisingly lengthy, even though the idea is pretty clear. So I think this is this week's proof that's strangely involved, similar to last week, where the Bolzano-Weierstrass, which is not a hard proof, but is certainly a very lengthy and detailed oriented proof. We're about to get that with the alternating series test. So before we get there, again, we're going to follow our usual pattern of first proving some facts about the behavior of summations, and then applying that to a series. Okay. Alright, so, hey, alternating series, so remember that means it's a series where we sneak in pluses and minuses, and so what we're about to verify is the following facts, that if we have an alternating setup and we sum to an even number, then it's the same thing as doing the summation. And likewise, summing to an even number, it's the same thing as pulling the summation apart like this. Okay. So note that this is effectively getting rid of the negative 1 to the kn and allowing us to directly work with the terms, which, again, a lot of these tricks that we're first establishing before we get into the theorems, right, they're basically devoted to making our lives easier. Right, and note for all n, so again, no surprise, these are just going to be very straightforward, easy inductive proofs. So, let's do them. Okay, and so if you're looking at these two and going like, well, okay, sure, but why? Right, the but why will be apparent when we get there. But for now, these are just things that are true that we're going to use. All right, so for the first one, right, plug in 1 for n. So then there's just two terms, and it's x1 minus x2. Right, because then we're going to make something alternating: x1 minus x2 plus x3 minus x4, yada yada yada. Alright, so that cleans up like that. So, assume it works. Replace n with n plus 1. Peel off the terms. Apply the induction hypothesis. And, oh, hey, look, that's precisely the next term added in. The end. the end, right. If you plug in n plus 1 here, you'll have 2n plus 2. So minus 1 will give you the plus 1. 2n plus 2, right there. There you go. Alright, so, again, nothing shocking here, at least. This is just, we need this. Let's take the time to prove it. The proof is super easy. And again, this is good practice for how to work with sigma notation, specifically how to actually prove things with sigma notation. Because, again, they are inductively defined, so any proof involving them would be with induction. Okay. Cool. Alright, and then fact 2 is very similar to fact 1, only... now our base case is n equals 2, so plug in n equals 2. There's your x1, your negative x to the fourth, and then this right here is just that term. Right, plug in 1, here's your positive x3 and your negative x2. And that's it. So the base case holds. So suppose it works. Replace n with n plus 1, peel off terms, and then combine things accordingly. So note that this would be the next term that is missing. Cool. All right. And note that you have an n minus 1 here, not an n. Thus why we need n to start at 2. Obviously, if n started at 1, this would be a absolutely invalid summation, although you actually can take that to equal 0, and usually that's not a problem, but sometimes it is. So I avoid that. But yeah, there you go. So again, these are not the most amazing proofs or anything, but these are things that we're going to use, and they need to be justified, and here's their justification, and yeah, it's not bad. Okay, cool. Alright, so with these two results in the bag, we can now go after the main event for today, which is the alternating series. So if you have a monotonically decreasing sequence whose limit is 0, then the series where I multiply the x sub n by -1 to the n plus 1 must converge. So this actually gives us a way of producing a series that converges based solely off of the fact that the limit is equal to 0. The monotone decreasing is also required as well, as we'll see. But yeah, so here it is, the alternating series. So when we talk about this in Calc 2, we call this a test. And it's sort of a test, because if you have a sequence that's monotone decreasing and its limit is 0, then you can verify this converges. So if you start with something that looks like this, and then you can go like, oh, this is monotone decreasing and the limit's 0, then we're good. Okay, now, why would this be true? Or why would anybody even think of this? Well, again, start writing out the terms here. You'll have x1 minus x2 plus x3 minus x4. Since we're monotone decreasing, x1 is the biggest thing. When you subtract x2 off of it, you'll just make it a little bit smaller. When you add x3, you'll make it a little bit bigger. When you subtract x4, you'll make it a little bit smaller. And note, the limit is going to 0. So you start at x1, and then you go to the left a little bit, and then you go to the right. But note, x3 is no bigger than x2. So adding x3 does not get you past x1. So what we're going to prove is that the sequence of partial sums here are going to be bounded. And that doesn't immediately get us the proof, because we don't have what you'll have is a subsequence that's monotone, which we'll see here in a moment, and so you got to use the subsequence that's converging and monotone and bounded above, and then from there you get the whole thing converges. So we'll see. But yeah, it's hopefully quite clear why this would even be true. But it does require a little bit of work, and so the trick ends up being the following. So we'll have two partial sums running around. We'll have the partial sums for the main series, so we'll show that this converges. And we'll let capital S be the partial sums for, so note this would be x1 minus x2, and then x3 minus x4, and then x5 minus x6, so on and so forth. So here we've just got the singular terms, and then here we've got the partial sums where we group the terms together pairwise. Now note, remember, Grandi's series says that I can't just immediately go, oh, well, this works the way I want it to. I need to actually directly work with it and work it out. So, yeah. So the plan of attack is we'll prove that S sub n actually has to be convergent, and then that forces Sn to be convergent. All right. And note the connection between the two. Capital S sub n, by our previous proposition, has to be S sub n to n, right? Because if we verified this is equal to that, and there's the connection. All right. Beautiful. So what we'll show is capital S converges. That guarantees that this subsequence of the partial sums converges, but that will then force everything to converge, which we will see in a moment. All right, so why does capital S sub n converge? Okay. So x sub n is monotone decreasing, which means this has to hold for any n, which means that holds. So, oh hey, all of these terms are non-negative, so this sequence of partial sums is monotone increasing. So that's really slick. We're using the monotone decreasing of a sequence to get a partial sums as monotone increasing. That's a fun little thing. All right. So what we'll now claim, which I already alluded to, these S sub n's never exceed x1, right? Because if we're talking about how the summation works, you start with x1, you subtract off x2, Then you add x3, but x3 is no bigger than x2, so when I add it back, I never get bigger than x1. And then this happens forever, because every time you subtract something off, the next term will add something just as big, so it will, if not smaller, so it will never push us past x1, so we'll always be less than x1. So we'll have something monotone increasing and bounded above, and thus we'll have something convergent. Beautiful. And then that's going to be the limit that we work with. All right. Okay. So the original series is assumed to converge to 0, so that means it has to be a bounded sequence, which means it's bounded below. All right. So since we are monotone decreasing, our hypothesis then tells us that its limit must be its infimum, and so this means that all of our terms are greater than 0. Beautiful. All right. So, what does that mean now? All right, well, S sub 1, which note is x1 minus x2, well, x2 is positive, so if I subtract it, I'm going to make myself smaller. There you go. So S1 is less than x1. All right, so hey, the case of n equals 1, what happens when n is 2 or bigger? Oh, good thing the previous proposition had 2 parts. All right, so the second part, take something that's 2, 3, 4, or whatever. Well, we know that S sub n, which is equal to this, and by the previous proposition we know pulls apart like that, for any k hanging out between 1 and n minus 1, because we have a monotone decreasing sequence, this needs to be true, so all of these terms are negative. So this is a sum of negative things, so this does not exceed 0. All right, and this too is also non-negative. This is non-negative because the infimum of the x sub n is 0, and thus we have that. So these are non-negative, and so then this is non-negative, and we're subtracting off something positive, so it's got to be that I'm just bounded above by x sub 1, as claimed. Beautiful. All right, nice. Okay, so we have now established that these things are convergent. They're monotonically increasing and bounded above, so they converge to something. All right, so let S be the limit of that. I claim that our original sequence of partial sums converges, and so our series is convergent, and that completes our proof. Okay. All right, so far, like I've said, this is not a difficult proof, but it is very involved. A lot of details have gone through here. So note, the first 3 slides of the proof here, right, this was all built off of 4 slides from before, proving all of this stuff is true. All right, and the eagle eye amongst you may have noted, well, so far, I've used the monotone decreasing. I haven't explicitly used the limit is equal to 0. I use that it's bounded below by 0. Right, but I haven't actually used that it converges to 0 just yet. We are, in fact, going to use it. So if the alarm bells went off and you went like, hey, wait, I don't really need the limit to be 0. Just seems like you need monotone decreasing and they're not negative. We actually do need the limit to go to 0. So we are using every single piece of the hypothesis, which we will now see. Okay. All right, so I claim that this the sequence of partial sums, the original one, converges to S. So, given an epsilon, I'm going to get you a capital N and show you that it works. All right, so we know that the capital S sub n's converge to S, and here it is, the x sub n's converge to 0. So you actually do need all of the hypotheses here. It's not enough that it's monotone decreasing and bounded below by 0. It actually does need to converge to 0. All right, so there's a capital N so that this works, and there's a capital M so this works, so obviously we take the maximum of the two. And for reasons, we need N not to be bigger than J, but rather be bigger than 2J plus 1. This will become obvious in a moment why we need this. So note, given an epsilon, the natural number we're looking for is actually going to be this one. Alright, so there are 2 cases that we have to consider. N is a natural number, and thus it can be even or odd. If it is even, that means it's equal to 2k, So 2k is greater than 2j, which gives that k is bigger than j, and j is bigger than n. Now, little s sub n, remember, if I plug in 2k into that, I'll pick up capital S of k. K is bigger than n, so this is less than epsilon over 2, which means it's strictly less than epsilon. Hey, there we go. That's not too bad. Right, and no, this is just effectively rewriting the fact that we already know this converges to S. Right, because again, remember, these S sub n's are not the sequence of partial sums of the original sequence, but rather just the even terms. So if n was even, there's no work to be done, because we already know that converges. So the case of it being odd is the trickier one, and that's why we need the 2j plus 1. Alright, so if n is odd, then it's equal to 2k plus 1. So now here, that guarantees that k is bigger than j, and thus bigger than n. This is bigger than j, and j is bigger than m, so 2k plus 1 is bigger than m. So note the k bigger than n is going to give us this, and the 2 j plus 1 is going to apply here. Blech. So there's the dump. Alright, so let's work through the deets. Okay, so we want to prove that s sub n minus s is less than epsilon. Okay, n is equal to 2j plus 1, 2k plus 1, so plug that in. Rewrite what this is equal to. Peel off a term. Note, 2k plus 1 bigger than m. Alright, now again, what is this? This is the 2k partial sum, which is equal to s sub k. So match the minus s with that, because we know we can make that less than epsilon. This can get paired with 0. 2k plus 1 is bigger than m, so we know that will be less than epsilon over 2. That's less than epsilon over 2, and bada bing, bada boom. Realest guy in the room. And the square ending the proof is actually off the slide, so. Oh well. Alright, but there you go. Proof completed. The alternating series test. There's the proof of it. Like I said, not awful. Very involved, though. Quite a few steps, a lot of details, a lot of ins, a lot of outs, a lot of what have yous. But overall, a not too difficult proof. And certainly the heaviest lifting we're going to do today. Alright, so with this in tow, we now produce a example of a conditionally convergent series. Okay, so 1 over n is monotonically decreasing and converges to 0, so we know this must converge. And since the absolute values of this gives us the harmonic series, which is divergent, we know that the convergence of this series is in fact conditional. So the convergence of this is not because the absolute values converge, the convergence of this is for some other reason. Right, and again, that gives you an arbitrary reason to care about this stuff, right? The convergence is based off of a fact other than that the absolute values converged. That's all conditional means. All right. So before moving on, I want to splurge a little bit here. I'm going to gush about some various mathematical things. So our next goal on our list of 4 bullet points, we have completed the second one. The third one is to prove the root and ratio test. Before we get there, I've got a few things I want to tell you about. Okay, so the first one is the value of this is known. And again, it's always a good thing knowing the value of a series. And hopefully you remember from Calc 2 that this is equal to log 2. And as far as I'm able to tell, this was proven first by a mathematician named Abel. So Niels Heinrich Abel is a mathematician that you have definitely ran into. But maybe not with the name, but you've definitely heard of things called abelian. And this is the namesake for abelian. Niels Heinrich Abel is the one who invented commutativity, apparently. He studied commutativity in the context of groups, and he was like the first one to really do that, so he gets it. In addition to the group theory stuff that he worked on, he primarily did analysis things, and as far as I can tell, he gets the credit for this. Or at least he gets the proof credit for this. There is a reason to suspect this is equal to log 2, based off of some stuff that we don't have just yet, particularly integrating a power series. But doing that doesn't immediately tell you it's log 2, it just gives you that it should equal log 2. But you need to use something called a Bell's theorem to guarantee that it actually is equal to log 2. So, as far as I can tell, we should give the credit to Abel here, but maybe, I don't know, Bernoulli did it or something. Anyway, I like giving the credit here for Abel. This has always been a fun fact. I always love that this is equal to log 2. It's just a interesting thing. There's a lot of series that have just very, very bizarre, like, oh, it's equal to that, what? Alright. Okay, cool. So, I'm going to continue to splurge here with some more fun mathematics. Okay. So, before we get to the root and ratio test, I've got another unsolved problem for you. Ooh, I'm just full of them. Alright, so we know that for p-series, this converges when p is strictly bigger than 1. And by the alternating series test, you actually know that this series converges for any p strictly bigger than 0. For p less than or equal to 0, it doesn't work anymore, which hopefully isn't too shocking. So that's kind of interesting that this one works when p is bigger than 1, but if I change what's up in the numerator, I can get it to converge for a smaller p-value. So, if I give you a function, can you determine and we stick usually to positive values of p so that this converges. Right here, if f sub n is 1, then we know p needs to be bigger than 1, and if f sub n is negative 1 to the n plus 1, we know that p needs to be bigger than 0. So given a function, is there a way for you to determine the values of p so that it works? Okay. This problem, as stated, is horribly unsolved because f could be any function you can think of, and yeah, good luck coming up with any sort of connection between f and the values of p that converge. But it turns out that studying such things is not completely fruitless. So these have a name. So a series of this form is called a Dirichlet series. So this is pronounced Dirichlet. The only way I remember how to spell it correctly is by calling it Dirichlet. So in my head, I know it's pronounced Dirichlet, but when I go to spell it, I say Dirichlet. So I know I spell it right. It's like Wednesday. When I go to spell Wednesday, I say Wednesday in my head, but out loud you say Wednesday. Yeah. Same thing here, right? Dirichlet. Dirichlet. Okay, so the following series, these are called Dirichlet series. Dirichlet, mathematician, he studied these, and the main thing that you're interested in with Dirichlet series is what's called its abscissa of convergence. Now, what a word, right? That's when you want to flex on people. That's when you really want to let people know that I'm a serious person and I do serious mathematics. Abscissa, the word, is broadly the distance from a point to the vertical axis measured parallel to the x-axis. It's like officially what the name of it is. But anyway, so a sigma, so that this converges when p is bigger than sigma and diverges when p is less than sigma. It's called an abscissa of convergence. Okay. So for example, the p-series have an abscissa of convergence of sigma is equal to 1. So when you're studying these things, this is primarily what you're after. Now, of course, if f sub n is any arbitrary function, good luck finding the abscissa of convergence. But for certain ones, the abscissa is known. For other functions, there's a neat little unsolved problem. You may know where this is going, but if you don't, Dirichlet series show up in a branch of math called analytic number theory. Ooh. You probably know where this is going now. So it turns out that these sort of series are very important, and also the end of the piece should immediately be setting off some alarm bells about another very famous function with another mathematician's name associated with it. But these are studied in a branch of math called analytic number theory, where you combine analysis and number theory, which is a very cool branch of math. And so it turns out that there is a very important function in number theory that you can put up here, and the abscisive convergence of that thing is very important. So, what is the magic function you put up here from number theory that gives you a very interesting Dirichlet series? All right, it's Morbin time. So the Mobius function is the mapping defined as follows, and this function has an absolutely ridiculous definition. Okay, so Mobius obviously is the planet Sonic the Hedgehog is from. But what is the function? So the function mu of 1 is defined to be 1, and then for any n bigger than 1, we define mu sub n as follows. It's negative 1 to the k if the number n is a product of distinct primes. And how many primes you use, that's the power of k you do. It's 0 otherwise. So if you have a prime factorization and there is at least a square showing up, then we spit out 0. So a number of this form, these are actually called square-free numbers. So that's another way of defining this, is that if your number is square 3, you do this, and if your number is not square 3, you spit out 0. So this, at first glance, this is just, yeah, sure, I bet you can do this, and I bet this is interesting. So if you actually compute some values of the Mobius function, you kind of notice that it seems pretty random in its behavior. So it starts with 1, then it spits out negative 1 because we just have 1 prime, so it's negative 1 to the 1. 1 prime, so it's negative 1 to the 1. 2 squared, so we are now in the otherwise category, so it's 0. 5 is prime, so it spits out negative 1. 6 is 2 times 3. So 6 is a product of 2 primes, so it's negative 1 squared, so it's 1. 7 is prime, so it spits out negative 1. This is got a square, so it's divisible. Right, this is 2 cubed, so it's equal to 0. This is 3 squared, so it's equal to 0. This is 2 times 5, so it spits out 1. Prime, so it's negative 1. 4 times 3, or 2 squared times 3, so it's 0. Prime, so it's negative 1. 2 times 7, so it spits out 1. 3 times 5, so it spits out 1. 16, that's a 0. 17, prime, negative 1. 18, 2 times 9, so we spit out a 0. 19, prime, so we spit out negative 1. 20, 4 times 5, so there's a square, so we spit out 0. 21, 7 times 3, so we spit out 1. So on and so forth. And if you're kind of looking at it, it goes 1, negative 1, negative 1, 0, negative 1, 1, negative 1, 0, 0, 1, negative 1, 0, negative 1, 1, 1, 0, negative 1, 0, negative 1, 0, 1. It's seemingly going to be spitting out random 1 zeros and negative 1s. Right? This, even though it's deterministic, right? It's got an explicit formula. Right, our inferior human brains look at this and go like, "Wow, it seems like it's just randomly spitting out numbers." Now, this very cool function has an incredibly interesting Dirichlet series, which is why you care about this. So it turns out you can prove the following: the Dirichlet series of the Mobius function times the P series is always equal to 1. This is not easy to prove, by the way. It's not horrible, but you need to build up a bunch of tools in order to get the proof of this. Specifically, you need to study something called the Dirichlet convolution, and then you need to talk about how that relates to infinite series, and it's a whole thing. So it takes a bit of work, but you can prove that the P series, first of all, these are obviously not equal to 0, so they have a reciprocal. 1 over them is defined. It just so happens that 1 over them is this power series. So this function that's seemingly spitting out random values of 1, 0, and negative 1 actually really isn't. It's spitting out 1, 0, negative 1 in a very specific way. So, pretty cool. Alright, so now that we know that that's true, what's up, Charlie? Can I finish recording?
I gotta tell you something. So, when me and Mom go outside, my Mom told me about this storm. It's just like clouds banging together.
Oh, okay. Cool. Alright, can I finish? Alright, thanks, Charlie. Okay. Alright, so, so the Dirichlet series of the Mobius function is very important. Well, first of all, it has this very neat little property. So the natural question now is, alright, well, hey, what's the abscisive convergence of this thing? So, note here, I'm implicitly telling you that, okay, the abscisive convergence is at least 1, because this is true for p bigger than 1. The conjecture is that its abscisive convergence is 1/2. Ooh, wait, when did we just talk about 1/2? 1/2 involved in a conjecture. Ooh. Did you know the Riemann hypothesis is a Calc 2 problem? Just gotta figure out when the series converges, and specifically, you just gotta figure out when the series converges, and we want the p-value to go down to 1/2. There you go. So, I remember I first read this in an analysis textbook. I think I've referenced it. Abstract Analysis by Andrew Gleason. So when he was talking about series, he offhand mentions, oh, by the way, this is equivalent to the Riemann hypothesis. And I was like, what? And it takes a bit to prove that it's equivalent to the Riemann hypothesis. But hopefully you can kind of see it, because this is revealing that this is the reciprocal of the Riemann zeta function. So if I can get this thing to exist for p-values up to 1/2, that means the Riemann zeta function has to be non-zero up until 1/2. So all the zeros are on the 1/2 line. There you go. So indeed, if you can figure out that this thing converges for all p greater than 1/2, you've solved the Riemann hypothesis. So what is currently known? Well, I already kind of let part of the cat out of the bag. So it is known to converge for p strictly bigger than 1, and that is super easy because the convergence is actually absolute. The Mobius function only ever spits out numbers between 1, only spits out 1, 0, and -1. So if you hit it with the absolute value, its absolute value never gets bigger than 1. So for p bigger than 1, it converges absolutely. So there's just nothing that you need to do there. P equals 1 is incredibly difficult, but you can prove that the series converges and it's actually equal to 0. This is incredibly difficult to prove. This is not easy whatsoever. It's actually not hard to prove that if this series converges, it has to equal 0. Because it's actually kind of easy to get bounds on the partial sums of this thing. Note, it's obviously not monotonic, so we can't just immediately be done because we have bounds, but there's ways of sort of... You can get lim sups and lim imps, and then you just gotta show the lim sup and the lim imp behave accordingly. But getting that it's actually equal to 0 is incredibly difficult, and in fact it's equivalent to a very famous theorem, which is the prime number theorem, which states that this limit is equal to 1, where pi of x is the function that spits out the number of primes that are less than your number x. So proving the equivalence of these two is actually not too hard, right, but proving that either one of these things exists is equal to what they claim they are is incredibly hard. The prime number theorem took a while to get proven. When it did get proven, the proof is like hundreds of pages. The current proof, the more modern proof, I think is about 8 pages long. 8 incredibly dense pages, but it's not that bad. But yeah, cool. Very neat stuff. So, if you want another road towards the Riemann hypothesis, this is probably the most accessible road, I think, to like a general math audience. Right? You're just trying to figure out if the series converges. That's it. Yeah, it's Calc 2. And there's actually a pretty good heuristic reason to believe this, because the Mobius function, again, is connected to the square free numbers, and the square free numbers are basically behaving like the amount of square free numbers is kind of related to the sum of 1 over n squared. So you can see the 2 kind of showing up, and yeah. So there's very good reason to believe this is true, because again, it's everyone's pretty much convinced the Riemann hypothesis is true. But yeah. Oh, side note on the Riemann hypothesis, it is decidable in the usual axioms of math, so it's not. It has to either be provable or disprovable. We can't be in the situation where there's no proof or disproof of the Riemann hypothesis, as opposed to the continuum hypothesis, which we know we can't prove or disprove using our usual axioms. Somebody sat down and took the time to prove the Riemann hypothesis is decidable. So there either is a proof or there is a disproof. So that's good to know. That you're not wasting your time. You're either going to prove it or disprove it. So that's good to know. All right, but I'm done splurging. Let's get back to um, our task at hand. So our third bullet point for today is to give some tests for absolute convergence, and hopefully you remember these. The root ratio test. All right. So, like I mentioned when we first started talking about limb soups, it turns out that the root and ratio tests are actually limb soups in disguise. So, you actually do not need convergence of the sequence here. You just need it to be bounded, and you need its limb soup to be strictly less than 1. And obviously, for the ratio test, we need all the terms to be non-zero. Otherwise, we're not going to have a good time. Alright, so note how the ratio test is stated. If the limb soup is less than 1, then we know we converge absolutely. When we learn it, we also learn that if this is bigger than 1, then it diverges, and that's actually not true. We kind of lie a little bit. So for limb soup, it's possible for limb soup to actually be bigger than 1, but you still converge absolutely, which we're going to see in a moment. So it turns out that for the divergence of the ratio test, you actually need to be a little bit more careful, and you'll see that in one of your homework problems. So it turns out that you need something to be bigger than 1, but it's not what you think it should be. Well, let me rephrase that. It has nothing to do with the limit. You just directly need the ratio here to be bigger than 1. All right. So how does this proof go down? Well, this proof is actually super easy. It seems like it's going to be awful because, right. As much as I love limb soup, so whenever limb soup shows up in a proof, I'm always like, oh boy, here we go. But it's never really that bad. All right. So our hypothesis lets us find a real number that lives between the two. Right. There's a gap, so we can find a real number between them. All right. And now, what is limb soup again? All right. Well, remember, limb soup is the infimum, which again, that's very annoying that it is an infimum, but right. It's really a limit of supremums, hence the name limb soup, but it's actually the inf of these soups. Now, because this is an infimum, anything strictly bigger than it is not a lower bound. So R is strictly bigger than it, which means it cannot be a lower bound for the a sub n's. So there is a sub m that is less than R. Otherwise, R would be a lower bound. I claim now that what I can prove is that x sub m plus k is strictly less than rk times x sub m for all k. And since this converges, because note, R has to be less than 1 in absolute value. Note where R lives. R is less than 1. And the limb soup over here is bounded, needs to be at least 0. Because everything involved is non-negative numbers. So R is at least 0, so its absolute value is less than 1. And then what do we have? Well, hey, this is going to have to converge because R is less than 1 in absolute value. And so, hey, this thing on the right converges. This thing on the left, by comparison, is going to have to converge. Now, there is a bit of details that I'm kind of hand-waving here. Right, there is a number that I'm ignoring because I can. Because note, m is fixed, so this is a single number. why does the series converge if I prove the converges for m plus k? Well, this means that there are infinitely many terms so that we're bounded above. The finitely many before this do not contribute to the convergence of the series. So you can just peel them off and be done. So I'm being a little hand-wavy here. There are some pedantic details that need to be filled in. You can go ahead and do it. Once you get this, we're good. So let's just prove this and be done with it. Okay. All right. So note that x sub m plus 1 over x sub n is less than am, right? Am is the sup of that set. So it satisfies that. And these are all non-negative. These are all non-zero, so they're strictly positive, so I can multiply them across. And hey, it works for 1. Now suppose it's true for some k. M plus k is bigger than m, so hey, we know this is less than am, which is strictly less than r. Multiply it over. And that's it. Proof's done. There you go, ratio test. We got it. Not that bad. All right, and this sort of trick occurs quite often in math, where you sneak in r to the k, and then you apply a ratio, and then you apply a geometric series argument. So you'll see this sort of trickery happening quite a bit. It occurs in something called the Banach fixed point theorem, which we're definitely not going to have the time to get to, but anyway, it's a very common thing. In fact, it's so common that it's exactly the same thing in the root test. So the proof of the root test is literally the same thing. So note here, again, you've got the nth root of these things are bounded, the lim sup is strictly less than 1, then the convergence must be absolute. Alright, well, it's strictly less than 1, so pick an r in between it. By the same proof, we can find an a sub n, so this holds, and then from there, you just do the exact same trick. It's going to be literally the same thing, so not particularly exciting, but yeah, and that's it. The end. And I'm not joking. There's not really much else to reveal here. It's literally just follow the same thing. You do have the nth root, I guess, to work with a little bit, but you basically get to ignore it. So yeah, there you go. All right, so basically following the exact same argument. And again, I'm not filling in the details. You can do it. It's basically exactly what you just did with the ratio test. So nothing too crazy. All right, neat. So hey, we now have proven the ratio test, and we've proven the root test. Yay! All right, now something that may have been offhanded mentioned to you in Calc 2 is that the root test in general is better. Now, the way they're constructed, you can probably see that, because the root test only involves the terms, and the ratio test involves a term and then the next term. So, in some sense, the ratio test is a bit more greedy. It needs a little bit more information in order to work. Oh god, what's going on with my computer? It's spazzing. Okay. But there's actually a way to make that this explicit, because something you can prove is that this is true. Oh, that needs to be a lim sup, not a limit. Where is that? Okay. So, this inequality is in fact true, and it's another example of, like, it's not a hard proof, but oh my god, is it involved. So the way you prove it is you suppose the inequality goes the other way, and it's strict, and you sneak a value in between the two, and a value in between the two cannot possibly exist, and then there you go. So this inequality then reveals that if the ratio test is telling you get convergence, so if this is strictly less than 1, then the root test will also work. So if the root test tells you convergence, that doesn't tell you the ratio test is going to work. In fact, you can concoct series where that happens. And so this is the classic example The root test specifically gives you something less than 1 strictly, and this also gives you the example of you mildly got lied to at the ratio test. It's possible for the lim sup of that to be bigger than 1, but it does converge. And like I said, for homework, you're going to see the actual situation where the ratio test will fail. But yeah, so there you go. All right, yeah. And like I said, this is not an awful proof. This proof is floating around out there. You can go look into it. But yeah. All right. One last thing for today. So broadly speaking, so far, what is this? Absolutely. All right. So let's finish off today with a brief discussion of okay, why is there really a reason to care about the difference between absolute and conditional? Okay. So, right, obviously there is a difference between them. We've given an explicit example. But is there a benefit to one or the other? So absolute convergence is nice because it's pretty easy to detect too. Because if you take the absolute value of your terms, then you've got non-negative terms, and we've got some ways of determining convergence of that stuff. Right. Specifically, we know that if the partial sums are bounded above, we have convergence. So absolute convergence is quite nice. But here's a obnoxious question. Let's suppose a series converges and you've got a bijection. Does the rearrangement converge? Now, in the finite case, the answer is yes. If I have a summation and then a bijection, then you can rearrange the terms and the sum will always work, right? That's just commutativity, and that's called general commutativity when you do that for a finite number of sums. It's worth noting that that is also an inductive proof, and it is not fun. I was debating doing it, but then I was like, no, that proof is very obnoxious. But yeah, so for a finite number of sums, you can rearrange the terms because you can just permute everything using commutativity. What happens when you go infinite? Ooh, you are not gonna like the answer. So, if you converge absolutely, then it turns out that go ahead, rearrange, you will converge, and in fact, you will converge to the original. So rearranging the terms of an absolutely convergent series does not change the value of the series. It converges, and it converges to what you want it to converge to. Yep. So, if you're absolutely convergent, you can go ahead and screw around with your series. And, right, this is just, of course, naturally answering the question of, oh, for a finite number of things, I can always do this. What happens when there's an infinite number of things? So, if you converge absolutely, then you can go ahead and do it. Now, this reveals kind of why you would always want to have absolute convergence, because it turns out that rearranging a series for more advanced applications, you're going to want to be able to do this. So specifically in a branch of math called measure theory, you're going to want to be able to do this, and that's where absolute convergence really matters. Absolute convergence also matters when you're in things called Banach spaces, but yeah. What happens if you converge conditionally, though? Oh boy, do things go completely haywire. So if you converge conditionally, then you can rearrange your series to converge to any real number you want. So, for example, the alternating harmonic, which we know converges to log 2, there is a way to rearrange it to make it converge to pi. Because who gives a shit? Welcome to hell, who gives a shit? So, this absolutely horrifying theorem was proven by Riemann, and it's called the Riemann rearrangement theorem. I'm not going to take the time to prove either of these. Our textbook does do the proof of this if you're interested. It's not that bad of a proof, but it's kind of one of those where it's like there's a step that's really relying on some facts about bijections from natural numbers to natural numbers that you really got to go to your way to prove that. Our book does not prove this. The proof of this isn't that bad, to be honest. So if you converge conditionally, that basically means there is an infinite number of positive terms and an infinite number of negative terms. And so what you do is you take your real number and then you take enough positive terms to add up past alpha, and then you start doing negative terms till you get less than alpha, and then you put in positive terms until you get bigger, negative terms until you get smaller. So you kind of just do an alternating series. Um, but the justification for why you can create a bijection that does that gets a little dicey. It's not the hardest thing, but the general idea behind the proof is pretty easy. Anything that converges conditionally must have a basically the an infinite number of positive terms and infinite number of negative terms, and then you can use that. So it's the outline of the proof isn't awful. The actual details is a little rough. And there you go. So it's worth noting this is actually a specialized case of the Riemann rearrangement theorem. The full-on version of it says that you can rearrange the series so that the lim sup of this can be whatever you want, and the lim inf can be whatever you want. So you can really go nuts with it if you want to. But yeah. All right, and with that, that's all I want to say about series for right now. We will revisit them when we get to integration. Specifically, you may be going, "Hey, we didn't do the integral test." Well, we haven't proved integration as a thing yet, so we'll come back to it. Yeah. All right, and with that, what's next? All right. Well, in our tour here of proving the theorems of calculus work the way we claim they worked, right, we started with the real numbers and we jumped straight to sequences and series, which was Calc 2. All right, well, what about derivatives and integrals? What about continuous functions? That's what we'll start talking about next time. All right.